unless you observe the null point. And again, same thing, how to observe the null point? When you see that the galvanometer has stopped showing any sort of deflection. Fine. So see, when the key is open, then you'll obtain one length L1. And same way, when you have closed the key, means current is flowing, circuit is active within here also. Then also you will obtain one more length L2. So now see, this was the formula which we got. Remember, I R1 potential E by R1 plus R into R1. This is the potential current multiplied by resistance. This term is your potential, and KL2 is a final formula. Small r is equal to L1 by L2 minus 1 into R1. So when I say R1, that is the external resistor. L1 is the first length that is obtained when the key was closed, was open. L2 was when the key was closed. And this R is your internal resistance. So if question comes on internal resistance, you all will be using this formula. Small r is equal to L1 by L2 minus 1 into R1. And rest of the questions are also based on formula only. Most of the theory questions which you have are based upon the principle. Even if just a direct question comes on the principle of it, V is directly proportional to L, you will be using it. Just the condition is that provided that your current should be constant. If your current is varying, like some equation, I is equal to 3t square plus 2t, then you cannot say potential is directly proportional to the length. Just be careful. If something hint is given or related to whether current is constant or not, then be a little careful and check whether same thing is coming or not. Otherwise, this is the basic concept. So Marita, if you are having some other questions as well, now practice other questions, whatever questions you have after seeing the basic theory. If you want, I'll share this with you. I'll write this page with you, or you can
Yes,
take
ma'am.
the screenshot also, whatever you want, let me know. And then also, if you're having doubts, please let me know. I'll share up all the questions with you, whatever you want. All right.
Yes, ma'am. Thank you.
Okay. Now class, we have to start with magnetics today. So see, magnetics also we'll cover in two parts. Because obviously covering the entire lesson is difficult. So what we'll do in magnetics, the Biot-Savart's law portion and all that portion, we'll take it today. And the portion that is left, that is your charge, single charge particle. That is very important because in your JEE exam, in your board exam, only circular part was there. Right, in your exam, only circular part was included. But in your JEE exam, motion under arc, motion under random path was included. So that we need proper time. So what we'll do, we'll cover that tomorrow. For today, what we'll do, the Biot-Savart's law and other portions, so that you have these portion, Biot-Savart's law, Ampere circuit law, applications of it, and then applications include your toroid and solenoid. This part we'll cover it today. From magnetic Lorentz force, because as I was saying, magnetic Lorentz force questions come to you based upon your arc formula and all these also. So that we'll see tomorrow. Now see, regarding Biot-Savart's law, everyone is aware of the Biot-Savart's law, I hope. Biot-Savart's law basically says that the way Coulomb's law says that for electric force is directly proportional to magnitude of both the charges. So magnetic field, Biot-Savart's law just talks about the magnetic field. So this is also directly proportional to certain things. If you are having a current element with you, a wire is there, current is flowing through the wire. So first thing, magnetic field's magnitude is directly proportional to the current. That is the first thing. Secondly, if I take a small portion from here, if I cut it and I take a small portion from here, so that portion will be what? It will be a part of this length of the wire where current will be flowing. We call this as current element. This is current element. And I have taken, let's say, a random point P I have taken, where I want to find out the magnetic field at this point because of this wire. If current is moving, magnetic field is getting exhibited. So at this particular point P, magnetic field should exist. So now what is happening? This small part is DL. This part, this is DL. So current is proportional to DL, current is proportional to I, and this separation between point P and this wire, I have taken it as R. So again, same way as your Coulomb's law was, same way as your gravitational, Newton's gravitational law was, this will also be following inverse square rule. So here also you will be getting inverse square rule. So once you have inverse square rule, it means your magnetic field is inversely proportional to square of the distance between them, that you call as position vector. If you call this directly as position vector, fine. And this position vector will be making some angle with the current element, let's say theta. So magnetic field is directly proportional to sine theta. So once you combine, you get B is equal to K ideal sine theta by R square. And the value of K is mu naught by 4 pi, which is 10 to the power minus 7. In your electric field, you had 1 over 4 pi epsilon naught, which was 9 into 10 to the power 9. Here mu naught is 4 pi into 10 to the power minus 7. Or mu naught by 4 pi, you can say, is 10 to the power minus 7. Now, this relation will be used a lot in your board exam preparation. Also, you must have seen Gauss is given in the questions. In your previous year questions also of JEE, you will see Gauss is mentioned. 1 Tesla is equal to 10 to the power 4 Gauss. Be careful with it, because sometimes it becomes confusing whether it was 1 Tesla as 10 to the power 4 Gauss or 10 to the power minus 4 Gauss. And with both of these values, options will be given. So those who will commit errors, they'll choose the incorrect option. Now, sources of magnetic Biot-Savart's law. Yes, regarding the direction. Here, direction is very, very important. So what you have to do, I'll just tell you briefly about the direction, because obviously in detail, we cannot study the directions as well, and all of you must be aware of the directions. If you are having a point, let's say we are having a straight wire here. At this particular point A, I want to find out the direction. So what can I do? I can simply do two methods. First method says that if I hold the wire in such a direction that the thumb is pointing upwards, right? If the thumb is pointing upwards like this, thumb is pointing upwards. So what is happening to the fingers? Fingers will be curled up like this. If thumb is pointing inwards, fingers will be curled up like this. So at this particular point, what will happen? See, if thumb is up, using your right hand, fingers are curled up. So at this particular point, your fingers are moving out of the plane. They are curling like this, right? So fingers are moving out. And same thing, and just the opposite thing if you take there. Here also, if you put the thumb out, so here what will happen? The fingers will be getting curled inside like this. So fingers are moving inside. Fingers are moving inside it. So how will you assess this? At the particular point, whatever is the curvature of your finger, that will give you the direction of magnetic field. This is one method by which you can use. That is by looking at the curvatures, whatever is the curvature, right? Just look at the curvature of finger. This is one method. Second method that is also applicable, that also you can use, is that you can place your direct fingers in the direction of current. Right now, what was happening? You were keeping thumb in the direction of current. Don't keep your thumb, keep your fingers in the direction of current. But how to keep your fingers in the direction of current? It can be in any direction. It can be, if I give you this particular direction and I give you this particular point A, then you can keep your fingers in such a manner that palm is facing downwards, in such a manner that the palm is facing yourself and fingers and nails pointing in the left direction. Or you can put your palm in such a direction that the dorsum surface, that is the back surface of palm, is facing downwards and the fingers there. Like this, you can have 4 directions for it. So which direction to choose? That you have to choose in such a manner that when you curl your fingers, it should curl towards the point. So in this question, if I keep my direction of fingers like this and point is downwards, And if I keep my palm in such a manner that the palm is facing me, so will I be able to curl the fingers towards that point? Right, I won't be able to curl it. So you have to keep your palm in such a manner that you're able to curl the fingers in the direction of that point. If you all of you try this also right now when you are listening to this, you are having your palm, right? Your nails are pointing towards the left as indicated here, because arrow is pointing towards the left, right? So that is your direction of current. But see, which direction you should keep. Your nails are pointing towards the left, that is fine. But whether the palm is facing you, palm is facing downward, upwards, or onto the screen, that is also, you have to choose between that. So how to choose in such a manner? You have to choose out of all the directions. When you will curl your finger, the curling of fingers should occur towards that point. If you keep your palm facing towards you, the fingers also will curl towards you, whereas the point is downwards. So you should keep your palm facing downwards, nails pointing towards left. Now when you curl your fingers, that will give you the direction. Thumb will give you the direction of magnetic. So this is how you can find out the direction of magnetic. These are some values for circular arc. See, for circular arc, this I'll tell you the applications of it. But first have a look at magnetic field due to infinitely long wire. So B is equal to mu naught by 2R, right? B is equal to mu naught by 2R is what? This is the magnetic field due to infinitely long wire. If you are having a wire that has extension to both the ends, if you're having a wire that has extension to both the ends, as in this is extending to infinity, the length is not definite, but you are asked to calculate at a particular point the magnetic field regarding it. Now how will you calculate? Right, the problem is that now how will you calculate? So what you have to do in these questions, so just remember the final formula, and that is very much sufficient. Just remember the final formula. So for infinitely long wire, just remember B is equal to mu naught I by 2 pi R. That's it. If it is semi-infinite means one end is closed. You had this wire where one was extending towards infinity. This was a particular point of calculation. So leave it as it is. This remains the same. It's just that the formula will become mu naught I by 4 pi R square. This is how the formula will become for semi-infinite wire. So magnetic field you have to remember for infinite wire, semi-infinite wire, and finite wire also. I think I haven't written it over here. No? See, you have to remember this for infinite also. Finite also. Finite, infinite. See, I'll write it here. If it's a finite wire, this will be mu naught I by 4 pi R. I was writing R. 4 pi R will remain the same, multiplied by sine theta 1 plus sine theta 2. Sine theta 1 plus sine theta 2. Now what is the sine theta and sine theta 1 and 2? Suppose this is the point. This is the finite end of wire. This is just the length of wire which you have. So it will be subtending certain angle theta 1 here. It will be subtending certain angle theta 2 here. The equation which you have obtained from here, infinite, this one, this is how have you obtained this. See, when this becomes infinite, so if you will join the ends from the infinite wires end to this point of calculation, that will be that we take it as 90 degree, because that becomes perpendicular only, right? Angle will not get deviated, whatever is the end. If you join it, it will become 90 degree only. It will become straight perpendicular. This point which is inclining right now, it will become straight. So we take this as 90 degree. And if this is also extending to infinity, this angle will also become 90 degree. So you just put 90 degree here, 90 degree here. So 1 plus 1, that becomes 2. And this 2 and 4 gets cancelled. So you have 2 pi. So actually this is a general formula which we put and see the cases for infinite wire, semi-infinite wire. In semi-infinite wire, we are getting this 4 pi r. How? Because in semi-infinite, only one end is here. Only one end is making an angle of 90 degree. So you have 90 degree, whereas other end is not present. The other end is not present. So what do you have? Only for this is making an angle 0 degree. Theta 2 is 0 degree here. That becomes 0. So you just have one. So only this part remains. So it's better if you remember this general formula, that will be better, because from that you can derive the formulas for infinite, semi-infinite, and rest of the formulas also. So what is sine theta 1 and 2? I'm repeating. This is a finite wire. At this particular point P, let's say I'm calculating, I will join the edges. This I will join the edges. So this is theta 1 and this is theta 2. So mu naught I by 4 pi r sine theta 1 plus sine theta 2. So whatever case you have, suppose angles are given, some random figure is given, you can use this formula. This is simply for finite if you have a particular length of wire. This you should remember. Apart from this, arcs, yes, arc you should remember. That is, I think, mentioned here as well. If you are having a circular wire is present, and at the center of the circular wire, we are calculating the magnetic field. So formula will be, if single number of turn is there, mu naught I by 2r. Suppose I have made 3 rounds. So into 3, because for 1 is this, so 3 it will be this. If I make one more turn, so into 4, like this. So n number of turns, you will just multiply it with n. So for at the center of a circle, you will be having mu naught I by 2r, n for n number of turns. Similarly, if semicircular coil, just half it, n mu naught I by 4r. If n is 1, means single turn is there, mu naught I by 4r. But if a random arc is given to you, which is subtending angle alpha, r is the radius here. This is the radius r and alpha is being subtended, because you will not be getting individual, you will be getting combinations of these. So n mu naught I alpha by 4 pi r, this will be the formula. Mu naught I alpha 4 pi r, and n will be the number of turns. Here also n is the number of turns. This is the main formula for a single turn. So just keep in mind whether 10 turns of semicircular arc, these types of questions are mentioned to you or not. One more case you should remember is this magnetic field on the axis of circular coil. See, if my circle is in xy plane, right? If my circle is in xy plane like this, so what will happen? This will be the same mu naught I by 2r as we have discussed. But suppose if I want to find out my circle, this is kept like this, and I want to find out at a particular point like this, in front of the center of it, not exactly on the center of it, in front of its center. So how will I find? So if I have to find out in front of its center, it means it is on its axis. So on the axis, derivation now you don't have to do, and the derivation is not necessary also, because whatever questions will be there will be based upon the vector addition and all. So that you will be able to do. You just have to remember this final formula, which is necessary for you to remember. Mu naught I r square divided by 2 by r square plus x square to the power 3 by 2. Now what is meant by this? Suppose point is lying here. R is the radius of the circle and x is the separation of the point from the center of the circle. That is the axial length. This is the length of its axis, or the point to which we are calculating. And according to the derivations, you will get it mu naught I r square by 2 into r square plus x square to the power 3 by 2. That is the formula. All these formulas you should remember. We will see questions also. Ampere circuital law is very easy. You just have to remember this statement that according to Ampere circuital law, line integral of magnetic field along a closed loop is line integral of magnetic field means B dot dl, integration of B dot dl. This is equal to what? Mu naught times, means mu naught times the current that is enclosed by the loop, that is I enclosed. So the way now in Gauss theorem, if you have, suppose in Gauss theorem, random charges present, which are some of the charges which are situated outside, but then you do not consider the charges which are outside, because you have to consider enclosed only. So even if it's plus q minus q inside and 3q here, still you will say flux is 0 because it is forming a dipole, right? So here also same thing will occur in terms of current. Even if you have plus minus current here, you have plus current minus current, you will consider these only, whereas 3i 4i whatever current will be situated outside. So I enclosed is important because you had seen also questions are based on I enclosed also, how much current is getting enclosed, whether you are cautious about it or not. So this is the basics formula of Ampere circuit law. One thing you should remember, which usually I do in the classroom program also when we have this for CBSE also. Calculate magnetic field of cylindrical wire in these two regions. So I would suggest you, it's better if you directly remember the formula for these, because most of the questions which I have seen in your previous year board exams, also in your JEE exams, in JEE exams, so definitely, another in NEET also, it's very much seen that rather than, obviously derivation will not be asked, derivation will be asked only in board exams, but this is used as a direct formula if a point is mentioned outside or inside the cylinder. So instead of using it as a direct formula, you can learn the derivation also, because modifications can be there. But I would suggest, if you remember this formula, B is equal to mu naught I small r divided by 2 pi a square. This one, this formula, and same way for outside, B is equal to mu naught I by 2 pi r. And the graph as well. Graph you will be able to plot by yourself also if you remember these two formula. This formula for inside, where r you are a is you are taken as the radius, and r is the radius of the Amperian loop. Right? All of you should know this fact, that the way we choose Gaussian surface when we are solving Gauss theorem, then we consider only that system with it. Same way in this magnetic field also, Ampere circuit law also, we have an Amperian loop. So this is the radius of Amperian loop. This is Amperian loop. All right. And here you have, this is also Amperian loop. Whereas your A here is the radius. This is the radius of cylinder. So these two formulas, those do not have, at least note it down. You should know these. Plotting of graph, questions from graphs will also be there from this topic. So in Ampere circuit law, this was the most important topic. The rest you have basic applications of it. This is the formula for solenoid. B is equal to mu naught. Ni is the formula for both. See, I'll tell you this separately. B is equal to mu naught Ni. This is the formula which you have to remember for both the devices, solenoid and toroid. What is solenoid? Just if you take copper or aluminium wires and just wound it in the form of helix, like this spirally, if you turn it, this is known as solenoid, whose magnetic field is mu is equal to B is equal to mu naught Ni. Mu naught is again the constant, 10 to the power minus 7 into 4 pi. I is current, N is number of turns. Now see, just difference is that in B is equal to mu naught Ni, this N for solenoid means, let's say L is the length of solenoid and N is the number of turns. So this will, N will become number of turns and capital N is number of turns. This becomes number of turns per unit length. Number of turns, this is length. And if you join the ends of the solenoid, what will happen? This is how what your figure will look like, right? This is how your figure will look like. Or if even if you curl and turn this inwards, this is how your figure is going to look like. This is known as toroid, just circular form of solid. So here also you'll be having a radius of this toroid and number of turns. So B is equal to mu naught and I is here also. But the value of this small n is number of turns per unit length. And what is the length of a circle? Circumference. So 2 pi r. This is just the difference and this is what you have to remember. I hope all these portions are clear. Rest of the portions we'll see it tomorrow only. Some questions, let us see on magnetic, same thing. I'll note down the question first. You will note it along with me. Then let me send your answers in the chat column. I'll discuss it. Yes, Ashit, I can. This Amperian loop part you want? These formula or the above part? Which part, Ashit, exactly?
This one.
This one.
Can you explain once more?
See, I'll explain you in this question because this question is important. See, class, when you have to find out magnetic field inside and outside. Now, see, already the solution is written, so I'll use these only. Now, when you have a point which is inside, right? When R is less than A means the point is situated inside. So, exactly this is what. Suppose this figure, let me explain you this figure. This is your wire. I have drawn it quite broad so that we can see and mark the things which are present inside. This is the radius A of wire. If you zoom and enlarge it, this is how the wire's edge is going to be visible. If it says R is less than A, it means a point within this. If let's say this is small r, right, this is within the wire, it means this is the wire that is enclosed within the Amperian loop. This is Amperian loop because R is less than A, any point which is taken inside, and this is actual wire. So see, if in this big wire, this wire which we have, like if this is the wire, current I is flowing across this wire, right? Across this wire, current I is flowing. That is what is written in the question. Question says that current I is flowing through it. So if I told you B is equal to B dot dl is equal to mu naught I enclosed, tell me, will the entire current be enclosed within this small portion? No, the part that is left here, this part of current will not be included. Only this part of current is included. So how to solve it? Just look at it. For the entire one, for this entire one which we had, which had the radius A, for this entire one, pi a square has current I. So 1 unit of area will be I by pi a square. So what is the amount of current which we need? Is this. So what will be the area enclosed by pi r square? So just multiply it. Pi r square will be I by pi a square into pi r square. So now at least we have the I enclosed. So now use your B dot dl is equal to mu naught I by r square by a square. This is now your I enclosed, this term. So when you substitute it, you will get this final formula. Whereas in this part, no, what has happened? R is greater than your this radius. The Amperian loop is greater than your cylindrical wire's radius. So what is happening? All of the entire current that is flowing through this wire is getting enclosed. So I enclosed is I here. Here the problem was that this was just taking a very narrow portion from it. Some portion of current which was there was left. But now here what is happening? We have taken a much more greater radius than the wire. So it will be direct mu naught I. So mu naught I. So B will be, length will be 2 pi r. Length of it, circumference will be 2 pi r. So mu naught I by 2 pi r. This is how you obtain both the formulas. Is it clear to all of you, this question?
Yes, ma'am.
Yes, Ashrit, is it clear to you? Okay, okay. No, Manita, just check your calculation. See, when it says no long straight wire, this means infinite. By default, it's infinite unless and until it is mentioned. Long wire, means infinite only. For toroid also, solenoid also, long solenoid means solenoid that is extending to infinity. Class, use this in the question. Di is given as I, that is current, I is current, by pi and d theta. Here you just choose a segment, then only you'll be able to answer the question theta. This part is very small. This part is very small portion, dB, which you are calculating. So from this one, resolve the vectors, then only you'll get the answer. Yes, resolving across this point. See, magnetic field due to this particular point, magnetic field will go in one direction. Then due to this the point, magnetic field will go. And theta is there, then resolve it then you will get it. Just check your answer once again. Yes, across point O. Across point O you have to. See here, class, how to resolve this. If you take a very small segment, if you take it here, let me read this part. This is the question that was given to you, right? Only this much part was given. See, if suppose this radius is given, let me erase the radius. At this particular point, you have to find it out. Now look here, class. Yes, I'll tell you how we got this. This also I'll tell you. Just wait. See, this is a very narrow segment of magnetic field if you will take. So one magnetic field, right, at this particular point along x and y if you take, or what you see, long straight wire, this is considered as collection of infinitely long wires that is placed across semicircular cross section. It's like infinitely long wires, collection of infinitely long wires like this. The collection of infinitely long wires, they are kept in the form of semicircle in this question like this. This is what this question is saying. So first of all, you have to find out the direction of the vector at point B. Fine. Firstly, you have to find out the direction of the vector. So we divide the entire current into elementary long particles. It means this is one, this is one, this will be generating one, this will be generating one, this will be generating. So at point A, because of this part, let's say one, it's divided. One magnetic field will be here because of this part, right? This magnetic field. We have divided the entire conductor into elementary part. And let's take no angle. Let's take angle with respect to here. Let's take it some phi. Let's take it. Fine, let's take it as phi. Random point. Same way, one magnetic field will be here also. Random one will be here as well. Along this, all these will be dB. This will also be phi. Then this will become 90 minus phi. Again, this phi. Same way, this will be 90 minus phi. And this will move on in the entire sphere, in the entire semicircle. Now see, if you resolve it, dB cos theta for all the portions of magnetic field. Here one magnetic field will be there, dB. Here one, all the magnetic field that are present within this part of this. See, let me divide this semicircle into two parts. This is the right part, this is the left. For all the right portion, this will be dB cos theta. And for if this is dB or this is dB, whichever part is there, I don't want to draw so many because the main thing will be not visible then. Fine. If these are so many magnetic fields, so what will happen? There also, this will also be dB cos theta. Can you see? Across x-axis, dB cos theta I cap, or you can say simply dB cos theta minus I cap. Both This is plus I cap, this is minus I cap. They are cancelling each other. You're getting net magnetic field as 0 along x-axis. But what about all these dB sine theta, sine phi, which are getting accumulated? I have taken it as phi. No? Let me take this as theta only. Because we don't need two. I thought we'll be needing two angles. We just need a single angle. So dB sine theta. So across y-axis, you have resultant magnetic field, which is integration of this dB sine theta. That's it. What you have to solve. See, net magnetic field will be what? Net magnetic field will be Bx plus By. Bx is already 0. By is integration of B sine theta, dB sine theta. Now, solving dB sine theta is a task. What is your magnetic field? How do you write magnetic field? Mu naught I by 2 pi r for wires, not for semicircle. We'll not use the formula for semicircle because you are taking it individually. Right. So mu naught I by 2 pi r, you will take it as 2 pi r. Now see, so just put in here in this formula magnetic field, which is dB. So you'll write mu naught I di by 2 pi r into sine theta, right? Suppose what will be current? So if you take a very, very small portion, let's say you have taken a very small portion. So current will be what? Current will be exactly whatever is the surface charge density present multiplied by the current that it is holding. Right? How will you calculate it? See, sigma is what? Sigma is the current per unit area, or you can directly write J also. J we write, no, we represent current density. How do we represent it? With the help of J. Current density, this is current per unit area. Right, this is current per unit area. So current per unit area, how will you calculate? Unit area is not given to you. So how will you calculate it? So you have to, if you go by the calculations, if this is your semicircle, let's say this way I'm drawing it, a very broad way. These are all, here you have all the location of all the individual infinitely long wires. So let's say this part is only small b, and this entire part was radius r given in the question, right? So how will you take it? If you calculate the area for this minus the area for this, so it's like pi, the entire part will be, this part is r only, not this. Not this. This is not given. Only this is given. No, this is not given. The length or the thickness of these wires. So how will you write the area? Area will be pi r plus b. This entire will become r plus b. This is r plus b whole square by 2. Right? Half you're taking it. Pi r square you take for a circle. So pi r square by 2. This is it, minus pi r square by 2. This is what you will take. So from here, you will be just, this is what exactly is your area. This is exactly what is your area, which you have to use in your questions. This is exactly the area. Now, even if you expand it, r plus b whole square, if you use r square plus b square plus 2r into b, and pi, let's say we have taken common. From here you have minus r square. And what is left? In the denominator also you have 2. This part is left. R will get cancelled. You have b square plus 2rb. Right? Only this part will be left. R square will get cancelled. Yes, now see. The thickness b which we are considering, no, this thickness b, this is very small. This is so small that this is not given even in the wire. Right? This is this much thickening in term of this entire. The radius is this. This is a very, very narrow portion, very narrow thickening that we have taken. This is very small. So even if you square it, it's like it's something 0.0001 centimeters, something this much thick. The circumference of the wire, in this manner, the wires are connected in the form of semicircle. So you can neglect this also. You can neglect this also, the thickness. So this becomes what? Area actually becomes this. You can neglect it. Now see, this 2 and 2 also will get cancelled. That 2 and 2 will also get cancelled. So area is ultimately left how much? Pi, right? The radius into the thickness. Till now, B, I am taking it as the thickness. Please try to understand concepts from this question only, because this is a very big question which has lots of questions modification from this part. That's why I've started with this one. It's a very lengthy question, but it has concept. I'll repeat it once also. Just try to understand it slowly first. So see, pi RB, you have it. Now area will be what? If you take a very narrow area, current is current is what? Current is simply current density, this part. DI is what? Current density is current density multiplied by area. So area you have as pi r into the thickness. Now pi r is what? Pi r is exactly what? This is the thickness which you're having a very small. How do you write thickness? How do you write the radius? If I give you, let me draw this arc separately. If I give you this very thin arc I have. The value is theta. This very thin arc we are having. The radius is r. And this is the thickness. How do you write it? RD theta. This is how do we write the thickness as RD theta, right? So this becomes RD theta. Understood? The small area, no, very small area of this, if you write the length of it, thickness of it, how do you write it? RD theta. That becomes the thickness of it multiplied by whatever is the thickness present. This you can write it, no, RD theta. If you have a huge arc, length of arc, this is how you write it. So because you can write it like this. So what is left with you? This part is left. Now see, if you write DI, current is what? Now how will you write current? Current, you can simply write it as DI. You are writing it as current density. Current density is current divided by area. This is how do you write current density? Current per unit area. So current per unit area is pi r square. So for all these single elements, you'll multiply with all the thicknesses which you have. So into this will become R B D theta, you will write R square. This R will get cancelled, right? This R square and this R square will get cancelled. See, this which was present, no, here. I by pi r square, I by pi into d theta. So from here you have I by r pi into d theta. Did you understand? This is pi r. Look here. This is, no, this is not pi r square. Wait, this is thickness we are telling, no? See, here we have thickness pi r into b, this part, pi r into b. And this is now, you have RB d theta if you rearrange it. So RB and RB cancel. This is what you have as I by pi d theta. This much of calculations you have to do. I'll repeat it. Don't worry, I'll repeat it. This is a very lengthy part. Now see, if you just substitute the value of I in the formula which was left, which was we were calculating, we got stuck because of DI. No information of DI was given. Now put it in this formula. B is equal to mu naught DI sine theta. If you put it, so magnetic field across Y will become mu naught by I was there. So instead of I, now I will write I by pi. Right? So there was already one 2 pi. See here, this was mu naught di sine theta by 2 pi r. I'll write this first. Mu naught I d sine theta by 2 pi r. Now see, mu naught by I'll write it as I by pi d theta. So that becomes 2 pi square. This pi will and this pi will get multiplied and this will become pi square r I d sine theta. Basically sine theta into d theta. D theta and integration. So integration of sine theta, everyone knows. Now see here, when you will resolve this, this is your answer along the y-axis. This is just what we have to do. Main thing in the calculation was finding di. I'll repeat it once more. Those who are having issues, you can understand if you're not able to understand. At this particular point, calculate all the, it's like very small long wires, very small. They are given to you in the form of semicircle like this. This is entire. The exact diagram also has these boxes made for these. These are all the infinitely long wires connected. Once you resolve it, x component cancels each other. Cos theta component cancels, only y is left. You have integration of dB sine theta. Now, in dB sine theta, at this particular point, we have reached. Magnetic field we have kept, sine theta we have kept, but the problem arises in di, calculation of I. So calculation of I can be calculated using current density. Current is current density into area. So area we did not know. So once you take their difference, just to find out this part minus this part will give you the area for this part, right? This entire this part. So from there you have the area as pi rb. Apart from it, if you use thickness multiplied by length, if you use that formula, thickness multiplied by length, thickness is r d theta for any length of r, and thickness is b. Already we have taken that thickness is b. So if you use these equations, current per unit area multiplied by whatever is the thickness you're getting it for small unit area. This is for entire, so di will be multiplied by di, right? So this you have it. Once you resolve it, you'll get this answer. Note it down. Wherever doubts you have, you can ask. It's a lengthy question, but most of the concepts are included in this. So usually all the other questions also know that have come in JEE. They are associated with these types of questions. Marita, this is the answer for second part, this one. 1 plus pi by pi.
So, ma'am, just a minute, I made a mistake.
Mu naught I by 4 pi r. Okay. 3 pi plus 2 by 2. 2 by 2 is 1 only. Okay, let me discuss it. Let me discuss. See, for the first part.
LCM.
Yes, answer for the first part, class. This is a very easy question. After the question which we have done, both the questions are easy. Out of these, this is the easier one. What is the answer for this? See, you will be getting two magnetic fields. One will be due to circular wire, one will be due to straight wire. Mu naught I pi minus 1 divided by 2 pi r. Yes, right, Krishna. Correct answer. This is how will we do. See, for circular wire, what will be the magnetic field due to circular wire? Mu naught I by 2r. But we have to keep one thing in mind. This is magnetic field. We have to write the direction. So for circle, what do? Use your right hand and curl your fingers along the sense of current. So thumb will give you the direction of it. So if you curl your fingers along this, 1 by r by 1 by pi plus 1. No, Marita, some error I think you are committing in taking the arc part, the circular part, I think. See, regarding here, so curl your fingers here what will happen? Your thumb will point inwards. If you curl your right hand in this manner, in the direction, that is, if you curl your right hands clockwise, thumb is pointing inwards. So I'll mark inwards. Regarding straight wire, formula is mu naught I by 2 pi r, because this is infinite, plus infinity to minus infinity. Now see, again we will use our right hand thumb rule. Place your right hand in the direction of current. If I place my direction, if I place my right hand in the direction of current, I have to keep it in such a manner that the curling of fingers occurs. So if I have to curl my fingers, that is, the point is upwards. So my palm also should face upwards, then only I'll be able to curl it. So if I place my hand in such a manner that palm is facing upwards, so thumb is pointing outwards. So I'll write this as outwards. Now what is the net magnetic field? Net magnetic field will be B1 for this plus B, or B circular one plus B straight wire, that is mu naught I by 2r. Let's say this is plus, no, so other one will be negative. If this is outwards, this is inwards, one has to be positive, other has to be negative. That is your sign convention which you choose, mu naught I, or you can even write it in terms of C. If it is moving outwards, if this is inwards, let's say this is inwards, right? 2r1, this is inwards, let's say. Or even if you take this as outwards, k cap, j cap, k cap, also in terms of k cap you can write, which is moving inwards, you'll write it as minus k, which is moving outwards, you'll take it as plus k. That also you can do. But net will be outwards only. Net will be inwards only. It has a greater value. So mu naught I minus mu naught I by 2 pi r, resultant will be outwards only. So the way Krishna answered it correctly, mu naught I by 2 r, I'm taking common, Krishna. This r I'm taking common. So 1 by pi, this much outwards, this will be left. Coming to the second one, in which you people were facing issues. See, this also, there will be now magnetic field due to this portion. Whenever you have a wire and along its axis you are finding out magnetic field, so magnetic field becomes 0 along the axis. Isn't this P point lying along the axis to this segment? Let's say this is segment 1. So magnetic field due to 1, this will be 0 because it is falling on axis. This is falling on its axis. So this is 1. Now second part becomes this curved wire, and third part is this. So this is second part, this is third part. If you find out B2, that is due to the straight wire. So due to straight wire, this is mu naught I by 4 pi r, and this is going to be inwards only. See, if you curl your fingers, you will get it inwards. All right, now the curved part is left, last part, the curved part. B3. So see, mu naught by 4 pi r, and we multiplied by alpha, that is the angle that is subtended. So how much angle is the arc subtending? How much exactly is this? Entire is pi. Pi by 2 you have subtracted. This was, right, 2 pi, from you there you have subtracted pi by 2. This part was 90 degree, pi by 2 you have subtracted. So how much will be left? 3 pi by 2, right? So this becomes 3 pi by 2, pi gets cancelled. You are left with 3 mu naught I by, how much? This will be 8r, right? 2 into 4. And this r, this is 8r. And I think direction is also same. And this, yes, curling is occurring in the same direction. If you curl your fingers of right hand clockwise, the thumb will go inwards only. So this is also inwards. So here you will add it. So net 1 is 0 only. This becomes mu naught I by 4 pi r plus 3 mu naught I by 8r, all as inwards. So net magnetic field will become mu naught I by 4r, 1 by pi, From here is left, and 3/8 from here is left. This is the solution for both of these. Note it down. Any doubts if you have, let me know.
Ma'am, it's 3/2, right?
Where?
In the answer.
Which one you're saying?
Ma'am, the answer to the second part, it's 3/2, right?
No, 2 into 4, 8.
Ma'am, the final answer.
In the final answer also, I have taken 4 common, no? Okay, from this you're saying it. Yes, yes. From here, if we take 4 also common, so yes, 2 will be left, right? You all can keep on leaving as you will write this part. Rest of the portions we'll do it tomorrow. So those who have completed, you can keep on leaving.